well, a week since our last lecture. So let's kind of go over the last topics of the projection-based method. So let's talk about first the algorithm that we're going to do, or that you're implementing at a high level, and then I'll talk about just kind of how to evaluate these fluxes. That if you're still struggling, and how to do that, how to store things. I'll talk about that. So first thing in the algorithm is to initialize all your variables, and your variables are u, which is the horizontal velocity, v, which is the vertical velocity, and p, which is the pressure, to 0. That's what you're going to ultimately solve for. In the middle, you're also going to get some fluxes, but we're going to store those. But these are the primary variables that you're working with. And then you're going to start a loop over time steps. So you start your time stepping loop. In that time stepping loop, one way you could do this is you first set ghost values for u and v. Okay, so I'll talk about what those are. So those are the ghost values outside the computational domain. Then you calculate your fluxes. So you calculate f, g, hx, and hy. Okay, those are stored at their appropriate locations, cell centers, or the nodes. Then you update. So once you have the fluxes, you can update u and v. And this is the fractional update. No pressure, no gradient of pressure term. And that takes you to from Vn to Vn plus 1/2. Okay. And that 1/2 just means that we're not done yet. We still need to correct it after we get the pressure. And then you solve your pressure Poisson equation. I'll talk about various ways to do that. And really, this is the discrete form of that pressure Poisson equation. This gives you the correction to the pressure field, which is really all that we need. And the job of this is to enforce that the gradient, the divergence of v at n plus 1 is 0. So that's what this is going to be doing in a discrete sense. If you correct the velocity according to this formula that I have next, that pressure Poisson solve will enforce that in a discrete sense, the velocity is divergence free at n plus 1. So gradient of p n plus 1 equal to 0. So that p n plus 1 is what gets used in the correction, and you take a forward Euler step and you do v n plus 1 as a function of the previous Vn plus 1/2, and then the pressure that you just solved for, and you keep repeating this. So this is a loop that requires evaluations of fluxes, solution of a linear system, corrections to velocities. Okay. The ghost values have to get set inside the time step, because remember that the ghost values depend on the solution inside the domain. Okay. So that is your basic algorithm for this, the whole kind of solver. Let's talk about the details of this. So let's talk about how to set the ghost values briefly, because we already talked about that, and then the flux evaluation on all the different fluxes that you need to evaluate. So first thing is ghost values. So you have to build arrays to store these the variables. So let's just say you have a computational domain that's a square, which is what you have right now. You're storing data at appropriate staggered storage locations. So you have the ghost cells. Where are the ghost cells? Well, the ghost cells are like the ones on the border, right here. They're like, you don't actually have the corner. You never need the corner ones. But you have all these guys here. And you set the u values. The u values, remember, are stored at the midpoints of the vertical edges. So the u values, let's draw a few of those, are over here. And you know that the u values are 0 at walls that are impenetrable. So for example, at the u value over here, u is equal to 0. And then you set the outside values. Okay, for the u values on the outside, the ghost values. So these ones right here are kind of the ghost values. You still store them, but they're not inside the computational domain or on the boundary. So at those points, you set the value u out equal to u in, where u in is inside the computational domain. So the kind of values that are involved are these values right here, those 3 values. Because you're across a wall, this is like the analog of what we did last time across a horizontal wall. This is not a vertical wall. What's an even function in terms of x is the u. And so the u value, you just set directly equal to what's inside the computational domain. And then similarly, you do that for the other wall on the right. So actually, I'll just be explicit for that. So if we have like a value here, that one's 0. So u equals 0 here. And then this is, let's say, my u in value. Then here, u out is also equal to u in. But then on horizontal walls, depends what the velocity of the wall is. So if the wall is moving, so I have a velocity of this wall, which is to the right. So this whole thing is moving with a velocity u wall. Then the values of u get set according to the u wall. So let's look at this one right here. Here I have, the u in is just designating for that particular calculation what is the inside value. And the u out on the ghost cell is going to be equal to 2 times the u wall minus u in. Okay, so that is, that's what's involved here, and these two ones are involved here. So remember that the computational domain is just this part right here, right? So this one's just outside, and you have to use the velocity of the wall to set that value. It's a horizontal wall, so the u velocity is an odd function, and so it's a linear function. It has to pass through u wall, and so by setting this value right here, we ensure that if you connect u in to u out with a linear function, it's going to pass through u wall at the midpoint. Okay. So those are, and you do the same thing on the bottom. It's actually the same formula, just that the velocity of the wall will be different for you because it's moving at half the speed. Any questions on the u ghost values? Okay. Let's talk about the v. Oh yeah.
Why did you say it moves at half the speed?
I think the bottom wall is supposed to be moving half the speed for double driven. Just the problem setup. The bottom wall is also moving in your case. It's not just a lid-driven cavity; it's a double lid-driven cavity, so that both the top and the bottom walls are moving. It creates some more interesting features inside the computational domain. Yeah.
In the question, we have two speeds on the bottom wall. So
Yep.
we look at like the Reynolds number and all. We refer to the faster speed.
Yeah, that's right. The Reynolds number is based on, it's defined based on u wall. So in your case, the bottom wall is moving at a speed that's u wall. Oops, that's u wall divided by 2, and the Reynolds number is given by u wall times the length divided by your kinematic viscosity, and the length of the computational domain is that length over there. That's your length L. Okay. All right, so let's talk about the vertical velocities. There's going to be a few fewer of these because they're very similar to u velocities. Where are they stored? Well, the vertical velocities are stored at these locations here. So, for example, I know here that v is equal to 0 because I cannot go through that vertical wall. No fluid can go past it. And so if this is my v in, then my v out is going to be equal to v in. This is now an even function of y. And so those are the values that get linked together. And then for a horizontal wall, I guess I should have made those not filled in circles, whatever. All right, so for for vertical wall, if I have the v values here, then my other value is right there. And if this is my v in, then my v out is going to be equal to just negative v in. My vertical walls are not moving. If they were moving, I would need to put that velocity into that formula. But v out is just equal to v in for the wall that's not moving, and then same with on the left side. So same formula on the left side. All right, so that gives you your u's and v's. Questions about the v's? All right, so let's talk about fluxes. Right, so I'm going to talk about fluxes. New picture here because I have too much stuff on that one. So flux evaluation. That's this. Remember, setting the ghost values was that first step in the time-stepping loop. Now you need to evaluate the fluxes, and I give you the size of the sizes of all of these for in terms of matrices. So let's go back to our computational domain, and I will draw the same things. Here, so okay, so it's my computational domain. And I'll just look at the inside values. I'll comment about what happens on the boundaries too. Maybe I'll just add one more layer just so that I get a little more room. This is still inside the computational domain. So it's part of the computational domain. But let's take a look at, I don't know, let's do the Fs. So the F evaluations, let's say that I want to evaluate the F right in the middle. So I'm going to pick a value, show the U values first. So here are my U values. And let's say that I'm looking at F at this point right here. Okay, so I want to know what is the value of f at that point. It's going to be u squared minus nu du dx. Okay, that's my f value. And I'll just label these u's as u left and u right. And so what you do is you first, okay, the viscous term du dx, that one is just going to be u right minus u left divided by h. Remember that h is the spacing between these cells. Okay, so the cell interval length. So central difference for that, it's easy. U squared is next. That's a convective term. We talked about that last time. You split this up as q times phi. Q times phi. Okay, where q is the average value of the two u's that are next to you. So they're it's the horizontal velocity. It's going to determine the speed of propagation. So for the q, you want to use u left plus u right divided by 2. Okay. The phi can be either the quick or the smart. I'm just going to assume that we're using, let's say, the smart limiter, just because I talked about quick last time. So it's going to be the smart of, okay, specifically ULL, UL, and UR, and this is if Q is greater than 0. So that means that it's going to involve these three cells, three values of U right here, where ULL is the left value. Okay? Now, okay, you have to evaluate Q first to determine which U's you're going to use. Are you going to use the ULL, or are you going to shift everything over and go the other way because the going the other way means that when you use like U or R, and that's if Q is less than 0. But Q greater than 0 means that these two U's tell you the flow is moving to the right. Now you bias with an upwind stencil, and that's either in the quick method or the smart limiter, but they both evaluate, and I'll explain that evaluation. So for now, it's the function that's going to give me this value of U based on these three values right here, some kind of quadratic interpolation with a limiter built in. Okay? And of course, if Q were less than 0, then you'd be interpolating these values. Okay? And again, you can use quick or the smart limiter. So that is how you evaluate the F. Okay? Let me do the G and the H, and then see if there's questions on those. So for the G, let's pick some values of, let's say I want G at this point. How do you find another color? So right there, I want G. And that's going to be V squared minus nu dV dy. Again, dV dy depends on the velocities in the vertical direction, but it's easy to do because we're going to use a central difference. So which values are we going to use? We're going to use the V values that are next to us. And of course, I could end up using that one too. I don't know. It depends on the Q value. But let's call this V top, V bottom, V bottom, bottom. And so dV dy is going to be just V top minus V bottom divided by H. V squared, this is going to be, again, broken down to Q times phi, where Q is going to be V top plus V bottom divided by 2. That's my propagation speed. And then the phi is going to be the smart limiter, or the quick method. And let's say that V is greater than 0. So I'll use V bottom, bottom, V bottom, V top. And that's if Q is greater than 0. So again, I evaluate Q first, and then I pick the values I want to use. I might end up using these guys if Q is less than 0. And that gives me the convective part, when I multiply those two together, of G. Yeah?
So like in this convention, we have 0, 0 as bottom left. And so you're taking like derivatives right to left, top bottom.
Yep.
Does it matter like versus going bottom top on the V derivative?
On the V derivative, you're talking about, okay, if I switch bottom minus top versus top minus bottom. Yeah, so it does matter in the problem setup. Like you want to make sure that you're consistent with which way your coordinate axes are going. And so I am, of course, you could rotate your coordinate system if you wanted to. I think I mentioned that in the beginning that I would be the most helpful if your coordinate system is this way. This one used to. And so if you start rotating your coordinate system, I might say good luck and just make sure you're consistent with your rotations. But for me, I like Y going up. And so you're free to make that choice. Obviously, we define our coordinate systems, right? The problem remains the same. But yeah, if you define the Y going the other way down, then sure, you would flip those two, and then you would store your matrices in the appropriate way, whatever makes sense to you. As long as you access them in the appropriate way, everything would still be fine. There's not too many like cross products that we take where we need to invoke like a right-hand rule or anything like that. But this will be consistent with what's in the notes also post processing. So I recommend doing this way. If you've gotten a long way and you're fine the other way, that's fine. Other questions? All right, let's talk about H fluxes. So that's your G, and we did F, so let's do H. And let's talk about HX. Pick a value maybe right here. Okay, so this guy right here, so it's going to be HX. That's the transport of X momentum in the Y direction, so it's a cross flux. So it's V times U minus nu du dy. Okay, and so the U values that are going to be involved are going to be right here and right here. And let's denote these as U top, U bottom, U bottom, bottom. And then I'm going to have V values also. So now you kind of have to mix things up a little bit. And I'm looking at VL and VR. Okay, so that's going to be your stencil. Depending on the value of Q, I might need to go up here also. But for now, let's just assume that Q is going to be positive. And what do I mean by Q? Well, this V, that is your Q. So Q is going to be VL plus VR divided by 2. The U, that's your phi. And that's your smart. And let's assume that Q is greater than 0. So U bottom, bottom, U bottom, U top. That's if Q greater than 0. And the U dy, that's easy. We have the values there for a standard central difference. Okay. So that's how you get HX. So remember, now you're kind of mixing things up. It's important to know which one is which. HX, what the transported quantity is X momentum. And that's why we say that's my phi. And it's being transported by the fluid moving upwards. So V is your transport velocity. That's your Q. Okay. And then du dy, that's good. That's straightforward to do. Okay. Now, if you did HY, then let's say that I want at the same point, because remember they're stored at the same locations. So right there, if I wanted HY, that would be U times V minus nu dV dx. And dV dx would be VR minus VL over H at that same point. So I'm reusing the same information there. Now my U is my Q, and that's going to be U top plus U bottom divided by 2. And my V is going to be now the smart. That's my phi. And that's my smart of, okay, I need one more. Let's say that that's VLL. So smart of VLL, VL, and VR. These are all V's. and that's if Q is greater than 0. I know it's got a little messy there, but just to show you the difference of how the HY differs from the HX. So for the HY, we determined the velocity using these U values, and then we interpolated the V. And for the HX, we used the V values to get our Q, and we interpolated the U's. But everything is on that kind of, it's like a cross-shaped, either horizontal or vertical. All right. That's your fluxes. On the boundaries, you should have no problems. I just mentioned that. So on the boundaries, the fact that you're storing ghost values is good because, what if I found that this value VL plus VR is actually a negative number? Then that my Q is negative, my smart limiter, I would need to use the value of U over here. And so that I do have a ghost value, right? Remember that I do set ghost values right there. So I have that data right there. Okay, now, when I evaluate H's right here, I've explained this a few times in the Piazza post also, to get the H right here, the convective part is just 0. You don't need to do this whole process to get V times U at the boundary nodes. Because on the boundary nodes, in your problem, you never have flow coming in, so one of these is always going to be 0 on all 4 walls. So at all 4 walls, the convective parts of HX and HY are going to be 0. Same with like the F value right here. Like you don't actually have a neighbor out there in case things were going one way, so the velocity is 0 there. So that goes away. Same with G on these walls right here. So boundary should not pose any problem with the ghost values that you have. You should never have to go outside of those definitions of the ghost values. Okay. Any last questions on fluxes? Good. Okay. All right. I'm going to move on to just briefly what is the smart limiter doing. You guys already implemented it, but for the purpose of this kind of flux evaluation, smart is referring to now using the phi value. So whenever you have 3 values in a row in some coordinate direction, could be x, could be y. There's your phi j. There's your phi j minus 1. And there's your phi j plus 1. Let's make them a little more equally spaced, just because I want to make sure I get the value halfway in between. This is phi j plus 1. The whole point of this is to get the value of phi, and unfortunately we used phi for the state value here, that's kind of the transported quantity, but we need to get it at j plus 1/2, which is right at that point right there. So it's at that j plus 1/2. And if you look at the formulas that are in the notes, you invert those, you see that phi j plus 1/2 is equal to phi j minus 1 plus, you worked with these on the previous homework assignment, phi hat j plus 1/2. So I know there's lots of phis going around in here. There's a notation that's used for the smart limiter. The phi without the hat is just the value of whatever is being transported, some kind of state, either a u or a v. Okay? And so you have it at 3 points. You want it right in the middle of the last 2 nodes. That's your phi j plus 1/2. It's written in that formula on the right as just based on the indicator definition. So this is the indicator definition. It's in the homework and also in the notes. It's written as some combination of j minus 1, j plus 1, and the value of the limiter, which is your phi hat j plus 1/2. That is what that kind of multiple case formula is. It's that has all those different, so phi hat j dot dot dot, 3 phi hat j dot dot dot, whatever formulas are, where phi hat j is your indicator. Phi j minus phi j minus 1, phi j plus 1 minus phi j minus 1. And sorry, I think I misspoke when I said indicator for this value right here. This is, of course, the limiter value that's returned by the smart value, the smart formula using the indicator, right? So the phi hat j is your indicator. That's like, imagine like the R from our SWEB interpretation of TVD limiters. So you look at your data, you compute your phi hat j, and then you apply the formula right here. That gives you your phi hat j plus 1/2, and then you use that formula in the definition of that limiter to get your phi j plus 1/2. So all of this is done to get the interpolation of this value of the state. You could alternatively use the quick method. That is fine for, should be fine for even the moderate Reynolds numbers. So that's just using these values. We did it last time, the quadratic interpolation. Okay. Okay, questions on that? Yes?
I just want to ask about notation. In the previous homework, I think we were like the phis, like j plus 1, just were used before, right?
We use, yeah, kind of, like, we use both. So like when we talk about the limiters, from just like a physical standpoint, like what is the, how is the velocity limited? Then we use like a U or V. And so I've gone back and forth. This is now for the general context of saying, look, we have all these transported quantities, these phis. How are they evaluated using data? And so, for example, yeah, for the F, the phi, the actual data is some mixture of the U's, right? So we're interpreting the U. So yeah, you could say this is like your ULL, UL, and UR. And then you're trying to get the value right in between, and that's going to be representative of this F evaluation. In the G evaluation, the 3 values that you pass into the smart limiter are the V's. But when you write the smart function, because you don't know whether you're going to be calling it with U's or V's, it's fine to use some other variable. So that's where we use actual phi.
Yeah, I think there's a confusion just before we used to have U's be a general quantity.
Yeah.
And now it's specifically the x velocity.
Yeah, so I mean, so yeah, when you write the function, this is going to be the general, a general quantity, and it's fine to do that. When you call it, then you give it the specific functions or the specific states that you want to interpolate. Same with the quick method. I'm going to go back there, but if you look back in the notes, the quick method was also taking 3 values and giving the last value. Okay. Other questions? Yeah.
For the calculation of hx is the transport of u in y direction, but why are we calculating the average of v value as v?
Yeah, so that's a transport velocity. So for hx, it's the transport of x momentum in the vertical direction. So if the fluid element, let's say there's, you're at some point in the domain, if the fluid is moving both to the right and up, then there is transport of x momentum occurring in the y direction, because the fluid packet that's moving carries with it its own x momentum as it leaves, let's say, a computational domain. So if it's leaving it, it brings, so there's a flux of x momentum due to the fact that the fluid is moving vertically. So what is being transported? The x momentum is being transported. That's why u is the phi quantity. That's what's being transported. It could be anything. You could be transporting a temperature. You could be transporting some concentration of something. But we're transporting x momentum, and we're transporting it in the vertical direction. And that's why the q, the transport velocity, is computed from the v velocity. So again, if we're transporting anything else in the vertical direction, we would still use the same q, but a different phi. So that's the breakdown. Whereas hy, the difference there is we're transporting the vertical momentum. So we use the vertical velocity. Remember, our density is always 1. And so that's my phi, and I'm transporting it horizontally. So my u is my transport velocity. All right, so that is the evaluation of fluxes. So we got the ghost values, we evaluated the fluxes. I think already, the actual update for u and the v I've talked about before. That just there's explicit formulas for that. The pressure Poisson solver. Let's just briefly mention a few things for that. How to evaluate that at corners. If you're going to make a matrix, this is your PPE, del squared P at n plus 1 is your 1 over time step, del dot V n plus 1/2. And evaluating that right-hand side is fairly straightforward. So for that, you take your UR minus UL divided by H plus top minus bottom divided by H. And we had this picture before. We have some cell. Then my U's are right here. So that's my UR, UL, and my V's are over here. So V top, V bottom, and my pressure is right here. That's my P. Okay, and then when you actually discretize this, then if you're doing something complicated like multigrid, then you have to do a little bit more work. But if you're doing just a matrix solution, then you have the nearest neighbors that you're going to be using. Yeah, that's pretty bad. I should have just drawn 4 squares, 5 squares. All right. So pressure at the center, pressure top, pressure bottom, pressure right, pressure left. And your del squared P that appears there is like your pressure top plus pressure bottom plus pressure left plus pressure right. And I ran out of space. That minus 4 pressure center divided by H squared. And that's your standard 5-point stencil. So it comes from the 1, minus 2, 1 in the x direction, same in the y direction, and you add those together. H is the same. It's the same as delta x and delta y. So that's your 5-point stencil. So now you can set up a matrix system and do the matrix for that. This is your right-hand side. When you're at boundaries and you need to use a boundary condition, remember that the boundary condition is the Neumann type. So specifically, let's look at corners. So what do you do on a corner cell? It's like, well, we have 2 boundaries. So you have the pressure here is the center pressure. You have pressure right. You have pressure bottom. And the Neumann boundary condition tells you that you would have a pressure center here. You're not actually storing this. I tell you that for the matrix system, just make the pressure be only on the interior cells, so you don't actually store those values. But the fact that they're PC is because you have a Neumann boundary condition. And so that means that on that cell, del squared P is going to be equal to P center plus P bottom plus P center plus PR minus 4P center divided by H squared. Because P top became P center, that's why it's P center. P bottom is still P bottom. PL, the left value is P center, and the right value is PR. The rest stays the same. All we did was just copied over the pressure. That ensures that across this wall, dP dx is 0, here dP dy is 0. So that's how you put my boundary condition. The options for the solver, if you make the matrix system, then you're going to have like A pressure vector equals right-hand side B. So this A is going to be an n squared by n squared sparse matrix. So n squared by n squared, not n by n, right? Your number of unknowns for the pressure is n squared. If you're solving on a 32 by 32 mesh, you have 1,024 pressures, right? And now you need to solve for those 1,024 pressures. So if you make a matrix, your matrix is 1,024 by 1,024. But yes, don't make it zeros, make it sparse, because you're not going to have that many entries. You have 5 point stencil, so on each row, you're going to have at most 5 non-zeros. So that's not too bad, right? 5,000 something entries, as opposed to over 1 million, if you store the zeros. You can do that. Just make sure that you pick one equation and to use p equals 0 for one equation. So yes, you're going to have to drop one equation any way you want. The first one's just as good as any other one, and set p equal to 0 at that cell. And we talked about how to do that. You replace that row of the matrix system with a 1 in the diagonal, zeros everywhere else. You replace the right-hand side with a 0 or whatever number you choose, and it doesn't matter. And then you just make it solvable. You then can invert it. Or you do multigrid with some kind of Gauss-Seidel or Jacobi method. OK. Any questions on the pressure solver? Yeah.
Now we're looking at the pressure solver, so I have no doubt in the fractional velocity.
Fractional velocity update. OK, let's just make sure. Before you mention that, let me see if I can bring that up. For the fractional velocity update, I think we had, so it was cavity flow, vorticity, and variable approach. OK. Did I actually write that update? Probably somewhere. Yeah, OK. Here's fractional velocity update. Question, yeah.
Will we need the derivatives for the fluxes?
Yes.
And for that, we would need the fluxes in the ghost cells as well.
OK. Yeah, so I tell you what the f sizes should be and the g sizes should be, and hx and hy, such that you have all the values that you need for your updates. So if you find you need another GOSA value, think about what is your actual, what are you trying to update? So for example, let's say that you're doing fx and h's. And you're trying to update a u here. Well, don't update this u because that u is 0. Like if you're on the left boundary, that u is 0. So you don't want to do that update, right? Now the v is going to be at these points, and you should have enough in terms of neighbors to do the v update there. Same with horizontal walls, vertical velocity. To do that update in the v, well, don't update the v. It's 0 at that point. So if you're trying to apply that to places where you know the velocity, then yes, you'll have a problem. But if you don't do it at the ghost points because you use the ghost cell formulas to get the ghost point values, and you don't do it on the walls because you have the values there, then same with the u's. I mean, the u values, you have it here, so you do the update. You don't actually store the u's over here, so you don't need to set anything there. Good. Yes.
So after the fractional update and after the pressure correction, do we have to update the boundary conditions for the ghost cells again?
Yeah, so you do because everything's part of the loop. So okay, wait, so you said after the
first fractional step.
The first fractional step, I see. Well, let's think about what you're going to use. So if you need to take the right-hand side, it's a good question. You don't need to use those values because the pressure right-hand side has a divergence of the velocity. And that divergence is computed from the nearest neighbors. And so your pressures are only going to be stored at the cell centers. So you have a pressure here. You're going to use V, V, U, U. You don't need the ghost cell values. Those are used for flux evaluations. So you don't need to waste your time updating the ghost values. You're right. I mean, that you updated the velocities, and now you want to use them again. But fortunately, you're not using the ghost cell values for the pressure Poisson equation. You're only using those for the quadratic flux evaluation. All right. For the residuals, there are 2 residuals. So I think we mentioned those last time. We had right. There are 2 residuals because we have 2 control volumes. I gave you one of these residuals for one control volume, which was this one right here. You have another one right here. What I didn't quite write down was that if you want to have the residual norm, like an L1 norm, you would sum together all of these Ri plus 1/2 j's, and then you would sum together all the Rij plus 1/2. And that's what you would monitor. So you would take the absolute value of each residual, sum it together, add everything up, and that is your convergence criteria. So that's the L1 norm. L1 just means sum of absolute values. Very easy norm to compute. All right, so that is the residual part. Last thing is post-processing. So for post-processing, to draw your streamlines, for that you need a stream function. You already have the x velocity and y velocity, so you basically run until things converge, meaning that your residual norm drops by the prescribed amount, and then you compute the streamlines. So remember that streamlines are contours of the stream function psi, where u is equal to psi y, which is, again, d psi dy, and v is psi x, negative psi x, which is negative partial psi partial x. Okay. And so the idea here is to store the stream function at grid nodes. Store psi at your grid nodes. So for example, you have a mesh right here. You have that on the wall, we're going to say that psi is equal to 0. So let's say this is the wall right here. So psi is equal to 0 on the wall. It doesn't matter if the wall is moving. The value of psi is something that you can use to compute how much flux goes between two different points. So maybe I should just draw that over here. So if you have, let's say, points A and B, and you have some kind of path between them, and the normal along the path, then the difference in the stream functions, psi b minus psi a, is what tells you how much of the flow is going between A and B. The v velocity dotted with the normal, the area flow rate between the value between A and B. Okay, that's if you have a divergence-free velocity field, that's going to be the property that you can use as a scalar value for the stream function. And it doesn't matter what path you choose. You could choose different paths, and you will always end up with the same value because, again, you're conserving mass or conserving area if your density is 1. And so that means that whatever's flowing through this black line is also flowing through this line right here because I could choose my control volume to be that in-between space. And so whatever flows in has to flow out. So this is always going to be the same, just by conservation of mass. And so that is a very useful property because we can apply it in a discrete way because we do satisfy conservation of mass in a discrete way. That is, if you have any velocities on a cell, if you look at one cell, actually, let me do it this way. So one cell, then I'm going to store u's and v's at these points, and they're going to be divergence-free in a discrete way. So let me just kind of explain that by showing you how to evaluate the stream function. So let's say this is my point right here. It's going to be my point 1/2, 1/2. So psi 1/2, 1/2. And this value right here is going to be my psi 3/2, 3/2. Remember, I'm at grid nodes, and my whole indices refer to the cell intervals or the cell centers. So that's why these are all fractional indices. The value over here, this is your v 1, 1/2. This guy right here is your u 3/2, 1. So, and this value of psi is psi 3/2, 1/2. Okay. So how would you get those values? You have to start somewhere. And you could start at a corner and say psi is equal to 0 there. And then from that, you can proceed to compute the next value over to the right. So psi 3/2, 1/2, which is going to be equal to psi 1/2, 1/2 plus d psi dx times h. How do I get that? I'm going from here to here. So the formula applies from this going this direction. That is what I'm doing when I do this update right here. I go from the left value to the right value, and I need d psi dx. But remember, d psi dx is just equal to negative v. So that d psi dx is my negative v 1, 1/2. So I have that value exactly where I need it, because that tells me the flow rate. Now, that's actually a wall, the first point. Then my v is going to be 0 there. That's fine. Okay, I'm going to be adding 0. That just means I'm not changing psi as I move to the right. But then when I move up, that value is going to be equal to psi 3/2, 1/2, what I just calculated previously, plus d psi dy times h. And so now I'm moving in this direction here, and that's my update formula. And my d psi dy is going to be equal to my u value. So u 3/2, 1. Okay, so that's precisely what I have for the u. And I get my psi 3/2, 1/2 that way. And then you can sweep by going up to the next value. So now you use that to go to the next value. You'll use the u value here, and then the next value, and next value. So you could go vertically upward and get all your psi values. And then you move over to the right, and you do the same thing, vertically upward, get all your psi values. Now, if you're comparing against somebody else's result, and they chose a different way, maybe they went first all the horizontal ones to 0, and then they used the velocity here to go up a step, and then they filled in all these. And then went up a step and filled all these. You should get the same values as long as you both converged to some tolerance. So basically, your values of the stream function might be a little bit different, but if you converge down to a certain tolerance, that tolerance is going to dictate how different the values are. So you can make the difference in your stream function values arbitrarily small, or at least down to machine precision. If you converge all the way there, it might take a while. So expect maybe some small differences. Yeah.
So v on the plot is 0. Right?
Correct.
So, and all those sides should be 0. So can you not just march that?
You can definitely just march up straight this way, for sure. Yeah, so that's why I said, this step right here is kind of a trivial step. This will tell you how to evaluate the stream function in a general setting if you have even if you had inflow, like an inflow boundary condition. But yeah, in your case, because you have an enclosed domain, wherever that domain is, there's no flow anywhere here. So psi is 0 on all the boundaries. So it's perfectly continuous. And the reason why you get the same values is that, if you consider taking this step right here, then you say, okay, now I have to use this this u and this v. How do I know that I get the same answer if I go this way? Well, look at what's going to happen. There's going to be a u and a minus v. The other one's going to have a minus v and then a u over here. And if you compare the psi 3/2, 1/2 value, those two formulas, you see they're exactly the same as long as you have the divergence condition, that this u minus that u plus this v minus that v is equal to 0, which is what the pressure correction enforces. So that's why the psi is unique. All right, and then you make a pretty picture, and you're done. Okay, almost. There's one more step, which is that finding the maximum. So let me just say a couple words about that. So like you want to find the core, and the core, the vortex core, is the location where that vortex is spinning about, and so that's going to be a local maximum or local minimum of your stream function psi. And to find that, what I think Piazza posted about that now. If you have a grid, and you found a value, let's say maximum value here, psi max. Well, there's some other psi values at the grid nodes also. And you could say that the core is like right there, and that's fine. That's, I think, perfectly acceptable for full credit, I think. I think I made this a bonus part, if I remember, but yeah. So if you want to get that bonus, then what you would do is you would do a quadratic solution technique for finding the maximum, meaning that you'd actually look at the neighboring values of psi and fit a quadratic to figure out where that is. So just, in 1D, how would that look? Let's say I gave you 1D data, and I said, find me the maximum, right? You could say, okay, maybe my function is doing something like that, and maybe the maximum is right here. Okay, that's maybe pretty bad. Let me try something else. Let's say that this is the maximum value right here, psi max. But maybe my data is such that I'm actually going like that, and to make this one lower, and so on like that. So maybe the maximum occurs slightly between these values. So what I'm telling you to do is to use these three data values, fit a parabola, whatever that goes through, and find that maximum that way. So basically, use neighboring data to do a quadratic fit. Okay, so you can do that in multiple dimensions also. So that's that bonus part right there for post-processing, that your maximum or minimum of psi may not be exactly at grid nodes, but you can do a better solution. It might be somewhere in between the cells. All right, then you have to find where those cores are, the vortex cores, and then once you have those, then you make a plot and print them out also, print out the locations. Okay, did I miss anything? I think that was everything for the homework assignment. Any additional questions? Yeah.
Regarding the streamline function, well, the result will be the same if I solve the vorticity as a Boltzmann equation.
You solve the vorticity. Okay, so you actually want to post-process that way. Depends what stencil you use. What you need to rely on, the fact that you get a same value for a stream function going different directions relies on the discrete conservation of mass at the cell centers. So the fact that del dot v is 0, when you use a second-order stencil at the cell center values. So depending how you solve, if you try to use the vorticity stream function formulation, and depending how you calculate the vorticity, what stencil you use, you might not get exactly the same result. But most likely you'll get something that is up to at least the discretization error the same. So you have something similar, you might not be exactly the same. Like if you compared your 32 by 32 result to somebody else's, you might not get the same value. But as you converge 64 and 64, it'll be closer. As opposed to this way here, if it doesn't matter which way you go, you're going to get the same value for a mesh as long as you converge down to a certain residual tolerance. Even though it might not be the perfect streamline plot, it will still agree independent of how you calculated that psi according to this stair-stepping. Okay. Any other questions? All right. Well, that's the end of most of the material. I have some special topics. So last chance for questions on this material. I think I covered everything. If I missed anything, it's not intentional. I think I got looking at my notes. Only I didn't talk about multi-grid, but if you're doing multi-grid, come talk to me separately. I did multi-grid. Oh yeah, maybe just mention a couple things before I start the extra topic stuff. If you go for that bonus thing, all the kind of fine meshes, the runtimes will go up quite a bit for the finer meshes. You're probably finding that, and so at this point, if you're considering implementing things in a compiled language, that's maybe it's a little bit too late for that, but it could definitely accelerate things. If you're working in MATLAB and Python, try to optimize as much as possible, vectorize. I think I had a question about is it okay to use some kind of vectorized techniques? Oh, sure. Anything's fair game for getting solutions as long as the code works and runs in a lot of time, which is between now and Friday. Right? So that's a lot of time. But yeah, so you could use compiled languages, you could use vectorization, whatever you need to do.